So, a couple of things. People were confused about the linear hypothesis, and they should be. So if you were confused, good. That means you were paying attention. Let me go over the linear hypothesis right now, maybe in a slightly different way. As you see these things in different ways, they begin to make more and more sense to you. The linear hypothesis says that if you double the amount of radiation, you have double the chance of cancer. If I want to give you cancer with one big dose, the odds that you get cancer are 0, because to give you 25 sieverts will kill you right away. You'll never get cancer. So I have to give you less than that. Suppose I give you 2.5 sieverts. Well, you may get sick, but you'll recover. But 2.5 sieverts is 1/10 of the radiation dose. So now you have 1/10 of a chance of getting cancer from it. If I give you 0.25 sieverts, you have a 1% chance of getting cancer. That's in addition to your normal 20% chance of getting cancer. So that's what it means. But when I talk about dose, for this course, look, I explained what I meant by a partial dose to the thyroid, but forget that. Right now, let's imagine that dose for this course is always a whole body dose. Clearly, if only half of your body gets it, you have half the chance of cancer. But I'm not going to ask you for calculations like that. Just take whole body dose. Now, suppose I have 25 sieverts, and I give it to one person. That person dies of radiation illness, no cancer. Suppose I take and I give him 1 sievert. Then he may not even feel radiation illness, because that's about where the threshold is. But he has a 1 chance in 25 of getting cancer, additional cancers. If I give that 1 sievert to 25 different people, we say then we've given 25 sieverts to 25 people. None of them will get radiation illness, because none of them got above the, one is just barely enough to get radiation illness. But we've still given out 1 cancer. It's 1 cancer for every 25 sieverts. Doesn't matter whether it goes to one person, to 25 people, or to 100,000 people. You spread that radiation out. You take your 25 sieverts and divide it by 1,000. So you get 25 millisieverts. And give it to 1,000 people, we expect 1 extra cancer. Doesn't matter how it's distributed, unless you give too much to one person, and then they're killed by the radiation sickness. So radiation sickness is not linear. You give 25 people 1 sievert, and you don't have anybody dying of radiation illness. It doesn't work that way. But cancer, we think, does. It's not proven. And if you look on the web, you'll find the argument is still raging. So it's not proven. And the public health people simply say, let's be cautious and assume the linear hypothesis. On the other hand, I think from looking at the biochemistry of what's happening, that the linear hypothesis is the most plausible hypothesis we have. It's not proven. It's not about to be proven for low doses. It's roughly true for high doses, like there were cancer survivors. There were survivors from Hiroshima who got very big doses, like 100 rem. And they survived their radiation illness. It's right at the threshold. And a lot of them wound up getting cancer. So in those very high doses, it's approximately linear. At the very low doses, is it still linear? We don't know, but based on the biochemistry, my personal evaluation is that it's a good bet. You will find people who think it's not. They say the body can recover. I love to debate with them. I think I have the stronger case, but it's an unsettled question. Not all questions in science are really settled. So given an unsettled question, what do you do? And that is something that people in the social sciences are perhaps more qualified to decide upon than the physicist, who doesn't understand people. So that's up to you guys. On the other hand, you have to have your physics right, and that's why you're taking this course, because the physics isn't that hard to get right. So that's the linear hypothesis. Basically, it says you let out 25 sieverts and you spread it out on 25 people. That means 1 sievert each. You spread it out on 25,000 people. That means a millisievert each. The number of cancers you'll get, if the total is 25 sieverts, is 1 cancer. It may be among 25 people, it may be among 25,000 people. That's the linear hypothesis. Some people say if it's spread out over 25,000 people, we should pay no attention to it. That's completely negligible. Other people say, look, that's still 1 cancer death that would not have occurred. Every person is an individual. That is a tragedy. Physicists cannot answer this paradox. I'm not sure even a social scientist can answer this paradox. One of public perception. Why is it when an airplane crashes and 50 people are killed, we pay more attention to that than the 200 people that were killed in automobile accidents? That same week, what do we get? We get about 40,000 automobile deaths a year. 40,000. Now we'll do a typical physicist-like approximation. How many days are there in a year? The engineer, the social scientist might say 365. The physicist will say, oh, about 400. Why? Because it divides easier. We don't like this. So that's about 100 per day. 100 deaths per day in automobiles. And yet a train crashes and 25 people are killed, and that's the headlines. What's going on here? Well, those are the numbers. Public perception is when they're concentrated in one place at one time, we are more interested in it. Do I understand that? No. Is it logical? You know, what is logic? Is it logic to worry about a death? We all die. There's no logic here. It's just a matter of the way society works. So the question is, should we worry about that one death in 25,000 more than we'd worry about one death among 25? You guys are more expert on this than I am. Okay. We're saying, so that's the linear hypothesis. I just wanted to repeat that and